Welcome back. In this module, we are going to cover a high-level introduction to machine learning. This module is not going to dive deep into each and every small aspect of machine learning. For example, we will briefly discuss what we mean by machine learning, what the different types of machine learning are. But the idea is that if you don't understand any of these topics, go back maybe probably to the course of Professor Andrew Ng and get a flavor of what these are. So, briefly, the outline. First of all, we will try to clear the air between what AI is, what machine learning is, and what deep learning is. This is something where people often get confused, and I would like to make it very clear before we dive deeper into the machine learning concepts. After that, we are going to provide a formal definition and more of an formal introduction to what we mean by machine learning. Then the taxonomy of different machine learning types, and these are basically the different types. We will go one by one in each of them. So this is a very common picture to differentiate the three different topics: the AI, the machine learning, and the deep learning. So what we see here is AI is basically a bigger umbrella. Within AI, we have machine learning in there, and within machine learning, we have deep learning. That is how these three should be understood. What do we mean by really AI? So, as the name sounds, artificial intelligence just refers to adding intelligence in a system artificially. That's it. If you're building a robot, if you're building a self-driving car, if you're building a system that can automatically invest money, any such tool that can be referred as an artificial intelligence tool. A program that can sense, reason, act, and adapt. And what machine learning is? Machine learning is basically the set of statistical algorithms that you implement within a system to make it artificially intelligent. Examples are linear regression, logistic regression, naive Bayes. There are thousands of algorithms that constitute the definition of machine learning. And what the idea of these algorithms is, these algorithms generally improve the performance of the artificially intelligent system as they are exposed to more data over time. These are data-driven algorithms. As you get more data over time, the performance of the system improves. So that is what constitutes machine learning. And what do we mean by deep learning? Deep learning is basically a subtype of machine learning. It's a small category of machine learning algorithms which primarily use deep neural networks, for example, CNN, generative adversarial networks, variational autoencoders. And the idea is that if you're making the networks deeper, the network has the flexibility of understanding different levels of information in different parts of the layers, and it becomes more interpretable and more understandable to the humans. And sometimes the performance of the way these systems work, we also try to make a resemblance between how the machine learning, how the deep learning system is working and how actually the human brain performs. So these type of strategies, they constitute deep learning. In deep learning, what we primarily study is how can we get a very deep network working, how can we get an understanding of different how can we get an understanding of what is happening in different layers of the network. These all things, they constitute the deep learning part. So I guess with this, we are now clear between what artificial intelligence is, what machine learning is, and what deep learning is. Then we are ready to understand more clearly what we mean by machine learning. In one line, machine learning provides systems the ability to automatically learn and improve from experience. So we have a system, it doesn't know anything, but with experience, it keeps on learning things, and there we have our machine learning system ready. Now, looking at a more formal definition. So we have a definition by Tom Mitchell. He's a very renowned computer scientist. And as per him, a computer program, so we are referring here to the machine learning itself. A computer program is set to learn from experience E with respect to some class of tasks T and performance measure P. If its performance at tasks in T as measured by P improves with experience E. It sounds a bit complicated, but believe me, this is a very beautiful definition. And in one line, it gives all the clarity about machine learning. So, a computer program is said to learn from experience E. What do we mean by experience? Later, I will explain through examples, but by experience, we mean for our system, if it sees more samples or more data from past, that refers to experience. With respect to some class of tasks T, what can be the task? Anything for which you want to design a machine learning system, that's the task for the system. And you always need to have some sort of a measure to evaluate the task. If you don't have the measure, you would never know whether the system is how the system is performing, and before you know how the system is performing, you cannot improve it. So the experience E, the task class of tasks T, and the performance measure P, these three things form very essential components of a machine learning algorithm. And I would like you to remember these three abbreviations, E, T, and P, because we are going to use it quite often in the next few slides, as well as in the next few sessions. So coming to a very simple example of a machine learning system. We see here 4 pairs, 2, 5, 4, 10, 10, 25, 100, and a missing number. The task is to basically identify what stands at the place of the question mark. These type of questions are very common in aptitude tests, but you might have never realized that this is actually a very good example of machine learning. What is the experience E here? The experience E here is basically the digit pairs. If you have a system, if you want to design a machine learning system whose goal is to identify this question mark, it has to first gain some experience. And here the experience is the set of the samples where you have the pairs known. So 2, 5, 4, 10, 10, 25, these are the experience samples for the machine learning model. If you quickly check, the last number has to be 250. Now, if we take the first sample, if we only know 2, 5, can we predict whether the question mark is supposed to be 250? No, because the question mark, the second number can be 2.5 times the first number. The second number can be first number plus 3. There can be different ways to define the second number if we have only seen the first experience. If we saw the first experience 2, 5, then we also see the 4, 10. We gain better clarity of what question mark will be. If we also see the third sample, we know even better what that missing number is. So these pairs where both the digits are known, these form the experience for the model. Our task here is to predict the second digit in the pair, and accuracy, for example, in this case could be just the performance measure in this case could just be accuracy. So if I give you many samples where you need to identify this missing number, out of those samples, how many you correctly identified, that forms the accuracy of the system. You cannot just compute accuracy based on one sample. I mean, for one sample, you might predict the missing number correctly by chance. And if you just take one sample to compute accuracy, you might end up wrong. So we need more samples to test. Now, this is a more elegant and very common example in the field of machine learning, the automated classification of MNIST digits. So we have here a lot of digits, handwritten digits. And if you look at carefully, each row constitutes one class of digits. So we have zeros, then 1, 2, 3, 4, 5, 6, 7, 8, 9 from top to bottom. Now, as you see, these are arranged. So we already know that these are labeled samples. So from top to bottom, we have the 10 classes. These are labeled for each of these images. From this grid, for every image, we know the corresponding label. Now, our goal is to classify the MNIST digits. Either there can be some of these for which we forget the labels, or we have some extra digits from outside whose labels are not known. So, and for those, we need to classify their labels, whether they are 0, whether they are 1, whether they are 2. So, looking at the experience, performance measure, and the task, starting with the task, the goal is to classify the digit. Now, the experience is here is the image label pairs for every image and the corresponding and if we know the corresponding label, that becomes an experience for our ML system. And again, classification accuracy can form the performance measure here. With these three, we can train our system to classify the MNIST digits based on the experience. And once it has learned, it can be used on samples where we don't know the label to identify what digit is in there. So that is again an example of a machine learning system. Now that we have understood what machine learning is, let's try to see what the different types of machine learning are. And to understand that, this example is already self-sufficient. This figure basically provides a simplistic view of machine learning. We have the big ball machine learning in the center. It is primarily categorized into three different types: supervised learning, the unsupervised learning, and reinforcement learning. I'll explain each of these in more details in the next slides, but these three are primarily the categories. There is also a less popular but still used category called semi-supervised learning, which constitutes somewhere between the supervised and the unsupervised learning, between these two. Then we have, for supervised learning, we have classification problems, we have regression problems. I believe you might know these terms, or these can be intuitively understood, but I'll also try to explain. And then these are some of the application domains of each of these. Then for the unsupervised learning, we popularly have clustering and dimensionality reduction. And for reinforcement learning, we have a lot of different tasks. We are not going to go into details of these small bullets, but we'll restrict ourselves to gaining an understanding of up to this level. So coming to supervised learning, as the name sounds, this type of learning for an ML system is performed in a supervised manner. So what is basically the supervised part? Where does the supervision come from? So the supervision comes from the labels that we have available with the different samples. Like for the MNIST digits, for every image, we knew what that class is. That is basically the supervision that we are giving to the model. So in other words, if your data is labeled and the labels are being used by the system to improve its learning, it constitutes a supervised learning algorithm. This picture gives a better understanding. We have an ML machine learning system that we want to train. And on the left side here, we have a lot of shapes, and we also have the corresponding labels for these. So we know that this is a rectangle, these are circles, these are triangles, these are hexagon. And when we provide the inputs and the labels to the system learns to map these inputs to the labels. And once it knows how to map the input to the corresponding label, it is trained. Then after that, what we give to the system is only the images. We only provide the images without the labels, and the system has to map it back to new labels. So for these examples where we don't know what shapes these are, the trained ML system has to label them. Like for example, here triangle, here circle. So going back here, we give inputs and the corresponding labels to a ML system during training. And once the ML model is ready, we only give input to the system, and the system has to predict the labels. So this constitutes the supervised learning approach. Here we are giving labels during training, and the labels are being used. That is very important. Now, putting it in an algorithm form, the input is labeled data samples. The task is to predict the labels for the unlabeled samples. So we predict the labels for unlabeled samples. That's the task. And the output is the predicted labels. The idea is just to learn the underlying mapping between the data samples and the respective labels. That is what supervised learning is. Now, this is the first category of supervised learning, classification, the task. All the examples that we have seen up to here, we have already shown these are classification tasks. But the one-line definition of classification is to make an ML system to assign any input to one of the K classes to each sample of the dataset. So each sample of the dataset has to be assigned to one class, one unique class. And note that this mapping is basically to a discrete set of classes. So you have n number of samples, you have k number of classes. Each sample has to be assigned one of the k classes. On the left, we have a case of binary classification. So we have these many samples, and what we wanted was that the model has to classify each sample into either class A or class B. And this is the example. So we have two classes, but realize that in classification we have a discrete number of classes. This is an example of multi-class classification. We have a lot of data samples, and the goal is to classify them into three classes. So we see the red, all the red samples are class A, then class B here, class C. This is a case of three classes, and we call it as multi-class classification. It can be 4 classes, 5 classes. There are classification problems with even more than 1,000 classes. So these are examples of classification. Some popular applications of classification are detecting spam in your inbox, whether a certain new email is spam or not. So we have two options, yes or no. That formulates a classification problem. Then cancer detection, yes or no. So that's again two classes. And analysis, good, very good, bad, very bad, average. We have 5 classes, but we can only choose one of them. So these are examples of classification problems. Another very common example of classification is dog breed prediction. So we have here a lot of samples in the data set, and each sample is labeled by one dog breed. I'm not aware of these dog breeds, but for those of you watching this lecture, if you are into dogs, you would definitely know these. For each of these images, we have a dog, a label of corresponding to a certain dog breed. And the goal is to train an ML system, which later, when provided with any new dog sample, is able to classify it into one of the dog breeds. So, for example, if we restrict ourselves to these, we have 8 different dog breeds. In the original dataset, there are more, but let's say we have 8 different dog breeds. The model will have 8 classes, and for every input image, it has to classify the image into one of these 8. That forms the dog breed prediction problem. So the task is, can we train an ML model to accurately identify the class for each dog image? The experience is these labeled images of dogs, and the performance measure again here will be the classification accuracy. There are more metrics, more advanced metrics, depending on how your data distribution is, how many classes you have, whether the classes are balanced or unbalanced. Based on that, there can be different performance metrics, but for the sake of simplicity, we are referring here only classification accuracy. Now, the other category of supervised learning is regression. The biggest difference between classification and regression is that in regression, the mapping from input to output is real valued. So you don't classify the input into k number of classes. Rather than that, you map the input to a real or continuous valued space. So, for example, we have here the green curve. This is a sinusoid curve, and let's say this was the original curve, the underlying model of a certain system. We generate data from here. So we take few samples on the green curve, and then we add some noise here. So these are the new samples that we have. Now, what this example is trying to resemble is how the real world system looks like. We fit a certain mathematical model into our system, but then there is some additional noise as well. So these are, let's say, the data samples that we have now. Forget the green ones for now. The blue circles are the data samples that we have. Now, what we want our ML system is, what we want from our ML system is to learn this mapping. So, for example, here the mapping is y is equal to sine x. So here we have y is equal to sine x. What we want our system is to learn this mapping. We will try to fit here standard polynomials. So, and try to see which order polynomial fits the best. And the m basically implies the order of the polynomial, maximum order of the polynomial chosen. So first we fit a polynomial with m equal to 0, the order 0. So we see that the slope is 0, and it's a horizontal line that fits. So this is just a line. The equation of the line can be written as y is equal to mx plus c, right? So m is 0. We have the c term, which can be the y-intercept. So basically we can have infinitely many lines from here to here, or even here. We can have infinitely many lines parallel to the x-axis, but this is the optimal line that we can fit. But we see that still there is a lot of error when we look at the red line and the blue circles. There is a lot of error. So there is a scope to improve. Now, before I go into the next picture, let me tell you, when we try to analyze the error, ideally we have to analyze the error with respect to the green data, because the blue circles also have some noise. We don't want our model to fit on the noise. So we see here that there is a lot this system there is a lot of scope of improvement. We still are very far away from either the green curve or the blue circles. We increase the order to m equal to 1. So this is the best line that we can fit. We have improved. With m equal to 2, we see that we don't fit the blue circles very well. I mean, we fit it quite well, not exactly, but at the same time we also see that our curve is able to approximate the original green curve quite well. Let's see what happens beyond this. When we increase to m equal to 9, we see that we have fitted over all the blue circles, but we have drifted away from the green curve. So what have we done here? We have learned a model that fits very well on the data, but it fits too well on the data that it has been trained. But it now I'll try to explain this. But it does not generalize very well. See, if for example, if we take this curve, we take a new sample which was not known during training, let's say here. The error in the new sample is not very large when we see the distance from the red curve. But if we take a new sample, let's say somewhere here, the error is very large, this gap. So what this implies is that when we take a very highly complex model, we are basically learning to fit on the training data, but not the actual model. We are fitting on the noise. That is actually overfitting. That is something that we do not want. We want our model to generalize well even on unseen data. We want our model to not fit the noise. We want our model to fit the underlying mathematical model. So here m equal to 3 is actually the best model. We will discuss this example later in a next session as well. But without going into more details, let me try to tell you this. So here we were fitting y is equal to c type of an equation. Here we were fitting y is equal to mx plus c. Here we are fitting a third order polynomial. For these, the coefficients of the polynomial, they can be real valued. So we are learning for an input, which are the data samples. We are for input, which are the data samples, we are trying to learn values of m and c, where c can be anywhere on this range. M can also be anywhere from -1 to 1, real valued. This is actually what regression is. We are mapping the input to real valued or continuous valued output. I guess it's clear, but I'll try to also explain this with a better example. So an example problem very commonly used in machine learning is to predict the housing prices based on previous data. So here our task is to predict the house price based on its floor area. So we have a lot of data samples where for every floor area, we know the corresponding price. Let's forget what the unit is. But for every a lot of for 500, we know the floor price. We know the floor price for different values of square feet. The regression problem here is to learn a mapping between the area of the house and the price. Now, if you realize this is not a discrete valued problem. It's not like you have it's not like you have a discrete set of prices that you can predict. It's a continuous mapping between the area of the house and the housing price. That is what regression is. That's what we see in the picture here. So the examples here are, the experience here is the example pairs of price and the floor area. Now, that was all about supervised learning. Let's try to understand what unsupervised learning is. So in unsupervised learning, we try to gain insights about the data using ML. and this data is unlabeled. So the biggest difference between supervised learning and unsupervised learning is that our data set in unsupervised learning does not have labels. And so basically in the training, we are not going to use any labels. The example here is uh, on the right, we have fruits, 2 apples, 2 bananas, 2 mangoes, and we want we try to divide these. We don't know the labels for each of these samples. What we want our ML system is to try to derive insight from the data, to try to understand the which samples are similar, which samples are not similar, and try to group them into different categories. So during training, we show the model a lot of samples, and the model splits those samples into different classes. So we have one set of samples here, the other set of samples here, the other set of samples. So once your model has been trained, if you give it a new sample, it's going to, for example, after this, if I give a new sample to the model, new sample of apple, it will put the apple in this category. If I give banana, it will put it here. If I give mango, it will put it here. So the model learns to divide the data into different clusters, as we see here, but it still doesn't know what these clusters are. Is it really useful for us? Labeling the data is very hard. Let's start from here. Labeling the data is extremely hard, and it's very expensive. We might think we can get the data labeled easily. This is the image of the dog, this is the image of the cat, by a lot of people just trying to annotate the data. That sounds simple. But if we have a lot of data set from very expert domains, for example, if you have data from the medical domain, if you're trying to label tumor, this is something that not everybody can do. And you really need clinicians, experts who can do that. And not everybody can and not everybody can accurately label such samples, and it becomes very expensive to label data for proper real world problems. So the labeling the data is very expensive. If we can derive insights from the data without labeling it, it's already quite good. And in this case, our machine learning system can split the data into different clusters. Once you have the data split in different clusters, you can analyze samples from each cluster to get an idea of each group. So that is the advantage of unsupervised learning. And the algorithm here for unsupervised learning can be defined as taking unlabeled data samples as input, dividing the data into k number of clusters, and then predicting the cluster out index for each of these test data samples. The idea is to learn the hidden representation of the unlabeled data set. So the model tries to learn what are the unique characteristics of each of these samples, the most discriminative characteristics, and based on those discriminative characteristics, it tries to split the data into different groups. I mean, for this simple example, we can think of the shape, the color as very important characteristics of the data set, and these can be used to split the data into different groups. And once you have a split, let's say 10,000 samples into 3 different groups in an automated sense, we can analyze a few samples manually, and then we can also tell this whole group belongs to apples, this whole group belongs to mangoes, this whole group belongs to bananas. So that is an example of unsupervised learning. But this is one of the ways of doing unsupervised learning, and this problem is referred to as clustering. I mean, we see here that we just take the data, we divide it into a set of clusters, that's it. But there is another category called dimensionality reduction. I will come to it after some time, but let's see another example of clustering. So formal definition of clustering is to group together samples that exhibit similarity in properties. This is also an example of clustering. It is in a supervised sense, it refers to segmentation, but here we can do segmentation of an image in a unsupervised manner. So the goal is to cluster these similar samples into the same class. So the model sees the pixel-wise characteristics of each pixel, and all pixels that resemble all nearby pixels that resemble to each other, it forms one cluster. Then we have the grass here that resembles each other, it forms another cluster. The dry earth part, it forms another cluster, and then the water forms another cluster. We see that there are some green grasses here, it again forms the part of this cluster. So the data has, each pixel on the image has been assigned a cluster. Let's say we have again the MNIST digits, but this time we don't know the labels for these digits. We want to divide the entire data set into 10 classes, 0 to 9. We don't know the labels now. We want to just divide the entire data into 10 sets. This can be done with clustering. There are algorithms which can take all the data, and then you just it just learns the similarity between the digits and then tries to separate them into clusters. There are cases where the digits look very similar. So for example, if it's hard to differentiate, but for example, it is possible that we have 9. So we have 8 here. So somewhere, I think this is 8, I presume. So we have 8 here, and probably this is 3. And we see that 8 and 3 share the boundary. The reason is that that the very distorted images of 3 can look like 8, so they will fall somewhere here. But still, it is possible to divide the data in an unsupervised manner into the 10 classes. So this is another example of clustering. Popular clustering algorithms include k-means, hierarchical clustering, spectral clustering, and deep learning based clustering methods. We will not go into details of these algorithms. If you're really interested to learn each of these, I would recommend looking at some online literature to understand how these clustering methods work. Now, the other other category of unsupervised learning is dimensionality reduction. It is basically to compress features and reduce the overfitting as well as noise. We are not talking about just reducing the size of the data for the sake of compression, but what we really want is to reduce the size of the data so that it only contains relevant information which is important for discriminating it from other samples. This helps to avoid any random noise and overfitting our model. So we try to simplify the features, reduce the irrelevant features as well as the noise. So from the book Machine Learning, a Probabilistic Perspective, this is the definition of dimensionality reduction. When dealing with high dimensional data, it is often useful to reduce the dimensionality by projecting the data to a lower dimensional subspace, which captures the essence of the data. This is called dimensionality reduction. We take the data from high dimensions, we project it to lower dimensions to a few set of features, and we only keep the essential features of the data. This is very popular for reducing the overfitting and the noise. We are not going to discuss too much details here. We will discuss these in one of the later lectures. But this is an example of dimensionality reduction from a geophysical example. So what we have on the leftmost, these traces, these long traces are called seismic waveforms, and each of these traces is expressed using 1024 data points. So 1024 data points for each of these samples. In the paper here, it has been shown that for the large data set that they had, each sample could be uniquely represented with just 32 embeddings. So with 32 values, each of these samples could be uniquely represented. Clearly, this is a huge compression for the data set. But this is not just for the sake of storing the data set to a lower dimensional space. The advantage is that in real world, when you are acquiring these seismic waveforms, there is a lot of ambient noise that you get in the data. And because of the ambient noise, it is very hard to characterize the exact information that you have in the data. With the idea of dimensionality reduction, it is possible to get rid of all the unnecessary noise, get rid of unnecessary features. So there are modes in these waveforms which are common in most of them. So if you want to really differentiate these waveforms, you don't need those modes. You only need unique characteristics of these. And those unnecessary modes, the ambient noise, everything gets removed and you project it into a lower dimensional space. This lower dimensional data can be easily analyzed, and good models can be built around them. And there is also a lot of research going on providing an explainable perspective to this. Can we provide an understanding of what these embeddings refer to? So it becomes basically very easy to analyze these lower dimensional data sets. So that is the whole idea of dimensionality reduction. Common algorithms for dimensionality reduction include principal component analysis, independent component analysis, autoencoders. We will look at these in later lectures. So semi-supervised learning. Semi-supervised learning is just the combination of supervised and unsupervised learning. Why is it useful? As I mentioned in one of the previous slides, labeling the data can be very expensive and very hard. So what semi-supervised learning does is it harnesses the power of supervised learning and unsupervised learning both. It takes some amount of labeled data, and it takes large amount of unlabeled data, because unlabeled data can be easily available. Labeled data is hard to achieve. There can be many different ways how you can formulate a semi-supervised learning system, but the underlying idea is that you need to use small amount of labeled data and large amount of unlabeled data. This is one of the ways to draft an semi-supervised learning system. So the input to the model is few labeled samples. We learn an initial classifier, and then we use this initial classifier to train more to label more data sets, and then we take the old originally labeled data set and the newly labeled data sets, combine them, and then we retrain the classifier. This whole process is done end to end, and that becomes our semi-supervised learning approach. So the model learns the mapping from some samples, but then to get a more detailed picture of the different discriminative features, it uses more pseudo labeled data during the learning itself. So that is one way we can draft a semi-supervised learning system. Now, reinforcement learning. In supervised learning and unsupervised learning, we show all the experience to the model during the training itself. In reinforcement learning, the model trains itself on the fly. So what I mean on the fly is, let me put it with this definition. In reinforcement learning, we design intelligent systems that learn to take right actions in a given environment. So we sort of, the popular term is an agent. So we take an agent, we put it in a certain environment. We don't give any information to sometimes you might want to give some a priori information, but the agent still doesn't know much about the environment. It starts operating, and it keeps an eye on the score that it gets when it performs a certain action. Based on the score, it gives feedback to itself for the next steps. So initially the agent doesn't know anything. It gets very bad scores, but eventually it learns how to survive in the environment and tries to maximize the score as much as possible. So this idea of taking feedback from the environment continuously and improving itself, that is what reinforcement learning is. And the most beautiful example, at least in my opinion, about reinforcement learning is the game of Atari. That was this video that was released by DeepMind. So I'll play this video for you. So this was from DeepMind, and they train the system to play the Atari Breakout game. What we need to know is that there was no prior knowledge given to the agent. And I think many of you might know Atari when you see this, but so basically this here, what we need is when the ball comes back, it needs to hit it from the bottom with this base plate. And this is after only 10 minutes of training. When the system has seen 10 minutes of game, this is how it works. And I think most of us can play better than this. But if a system has been trained for 120 minutes, it already plays like an expert. And so we see now the model knows how to play this game. I think even many of us might not be able to match this performance, but this is how an expert would play this game. See, I mean, it can continuously identify the trajectory of the ball. So that is what you can do after 120 minutes of reinforcement learning system. And after 240 minutes, what we see is that the system starts playing the game at a completely different level. It exceeds the capability of the expert. It now it knows its environment so well that it has now started digging a tunnel at the corner, and after it dug the tunnel, it has achieved a lot of points in a very small step. So it puts the ball from the tunnel, and you see that it can play the game at a level which we even cannot do. At least me, maybe some of you can play it better, but that is the idea of the reinforcement learning. Can train a system to play such complicated games as well. And this was a very old example. Now we have also more elegant examples, and we keep on hearing news that the reinforcement learning system has beaten the top chess players or the top X players, Y players. That is how reinforcement learning operates. And this is not only in games. Reinforcement learning is also gaining applications in more scientific domains, more practical problems which can create impact on the society. And this is an emerging field. If you're really interested to in developing such automated systems, such games, I would recommend look at reinforcement learning in more detail. This might be something of interest for pursuing a future career. So looking at it more formally, reinforcement learning again is design intelligent methods that learn to take right actions in a given environment. Some important components are we have the agent, we have the environment. So the agent takes decisions based on past rewards. The environment is the physical world in which the agent operates. And for every action that the agent takes within the environment, it receives some feedback in the form of reward. And based on the reward, the agent takes a new state, and that's how this whole feedback loop operates. And eventually, the agent learns to thrive in the environment. So that was my last slide for this module. I guess with this, now you understand what machine learning is, what are the different types of machine learning methods